In this video, I want to talk about a few of the more interesting things we can learn from a stress-strain plot. So as a reminder from last time, if we plot the stress, meaning the force divided by cross-sectional area, inside some material, like a bone or a ligament or something that we're pulling on, as a function of what its change in length is, as a percent, we get this very characteristic shape. And it's got a few different features that we can maybe take interest in. There's this little region down here called the toe region. Not every material has a toe region like this, and when we talk about bone versus cartilage versus ligaments and tendon, we'll understand why. But then there's this big linear region right here. And if you want to imagine what's going on in the material, let's say we're imagining our Achilles tendon, and it's kind of like a big rubber tube. When we start out, it looks like this, and then as we pull on it, what happens is it gets longer. And I'm going to do my best to draw exactly what's actually happening. So it does get stretched out a little bit in the middle, of course. Usually, though, these changes are small enough that we kind of neglect to really bother with what that change in cross-sectional area is. But conceptually, what's going on is we're pulling on this, and it's changing its length from, 4 inches to 5 inches. That'd be like 25%. 25% strain for, maybe 150 pounds of force, something like that. And during this period, this linear region, it's behaving just like a spring, just like a spring in your suspension system in a car, just like a hair scrunchie or a rubber band, things you're very familiar with. Then once you get up to this point right here, which has a special name, the elastic limit, maybe I'll write that down. You start to deviate from that linear trend. And what's actually happening in this region has a name, it's called the plastic region. And what's actually happening is that the material is physically changing. And in the case of a tendon, it's physically being damaged. So we'll see this when we look at tendons in detail, but if you could zoom in at the microscopic level, you'd see little strands of the collagen fiber that make up the tendon starting to break. Up here is something called the ultimate stress. Which is the highest amount of force that this material will ever support. And then down here, you have the failure point. This is when the material is getting macroscopic damage, and then eventually you get failure. Like an Achilles tendon rupture, for example, you end up here. Inside the body, you really want to stay down in this area. Once you get up into here, you're doing some real serious damage. Now, we already talked about how the slope of this curve tells you the stiffness. There's a technical name. You don't need to know this part, but there's a technical name for the slope of a stress-strain curve. It gives you something called the Young's modulus. Sometimes also called the modulus of elasticity. It's just a version of stiffness that's like normalized to the cross-sectional area. But you may encounter that in literature about the relative strength of bones and tendons and so on. There's another interesting property though, which is that the area under this curve. So let's say we stretch our Achilles tendon up just to this point. We don't want to break it. Just stretch it up to here, and we hold it. This is like maybe you're doing a calf stretch, right? And you stretch your calves, and your Achilles tendon is stretched out, but not ruptured, because you didn't stretch it too far. The area under this stress-strain curve. So, like, if again, this is a calculus thing, the integral. But if you're not in calculus, don't worry about it. This area, if you could measure it, that amount is exactly equal to the amount of energy stored in the tendon. The technical term is the strain energy. But what that means is if you stretch out a tendon, you get to store up this amount of energy in it. And then when you go back down, you get to release it. This is why we have tendons, and this is why the Achilles in particular is so long and so thick. It's because it turns out to be very efficient for walking and especially for running to store up a huge amount of energy in that tendon and then release it. So there's another piece to this, another complexity that I want to sketch out, and I'm going to continue from what we were just talking about. Let me duplicate my axes here. Strain on the x-axis, stress on the y-axis. So we were talking about storing up energy in the Achilles tendon. So you stretch the Achilles tendon out, maybe to here. And then, so this is like stretching your calf, and then you let that energy back out. Something interesting happens. So you've stored up this amount of energy, right? But when you go back down, an ideal perfect spring, you would just go right back down the same path. What happens in all real physical tissues in the body is you go down like this. Back to normal. Back to like unstretched. So on the way up, we're stretching and we're going up a curve like this. And on the way down, we're going down like this. This is a phenomenon called hysteresis. Greek word. Hysteresis. And given that we know that the area under this curve is the amount of energy stored on the way up, pay close attention to what I'm shading here. This area is the amount of energy stored, and I'll choose a different color. This is the amount. Notice how I'm shading under the bottom curve. This is the amount of energy returned. So you can probably see how the difference between those, meaning the area between these two curves, this little slice, is the energy lost. Technically it's the energy lost to hysteresis. Now in biological tissue like the Achilles tendon, usually it's maybe 5 to 10%. Some studies say maybe up to 20, 30%, but the most commonly cited figure I see is about 5 or 10%, which is not too bad. You may remember, by the way, the beginning of this course, I introduced one of the topics I used to motivate what we were doing is how new developments in running shoe technologies allow people to run faster. And that actually has to do with this hysteresis. Better running shoe technologies have less energy loss. So maybe old-fashioned running shoes, if you make a quick plot of that, maybe it looks like this. So you go up on the way, up on the way up, and then down on the way down. Yeah, something like this. And that area is the energy lost. Old-fashioned shoes, maybe it's like, 30% energy lost. Newer, nicer shoes, there's two interesting things about them. One of them, they are not quite as stiff, and the other one, they lose less energy to hysteresis. Maybe only like 13% in the top of the line shoes these days. So 2 big things that we learned from stress strain curves this time around. Number 1, The area under the curve is the amount of energy we store when we are essentially stretching out that spring. Number 2, in any real tissue, when you go up, you store more energy than you can get back out when you go back down. And the difference between those two, that process, or the fact that you lose that energy, is called hysteresis. The difference between those two areas under the curve is this green thing here, and that's the amount of energy lost. Usually we'll express it as a ratio of the original amount of energy. So that's 2 of the more sophisticated things you can learn from a stress strain curve.